Can anyone summarize what we have discussed in the last class? Anyone? Am I talking to you or some others? Akhilesh, Ratan. Who is this guy leaving? Who was that guy? Am I audible here?
Sir, audible, sir.
All of you, please switch on your webcams. Switch on your webcams, everyone. Then I will start teaching. Only 4. What about others? Okay, you switched off. Okay, in the last class we have discussed about the 3 modes of heat transfer. What is conduction, what is convection, and what is radiation. You can switch off your webcams, ma. Please. Yeah. We have discussed that conduction heat transfer is due to temperature gradient in a medium, in a stationary medium or media, or conduction heat transfer is the mode of heat transfer by usually by means of physical contact within the same substance due to temperature difference from one end to another end, and heat transfer by means of one molecule to another molecule or between one surface to another surface in contact. Okay, and due to the temperature difference between the two bodies, usually what happens is you will be having heat transfer from one body to another body. And convection is a mode of heat transfer between a surface and a moving fluid. Either the surface will be at a higher temperature and moving fluid will be at a lesser temperature, or sometimes the moving fluid will be at a high temperature and surface will be at a lesser temperature. Can you tell examples for hot surface and cold fluid and cold surface and hot fluid? Anyone? I had told you in the last class itself. Anyone?
Sir, engine,
Yeah, engine. Engine as
sir,
an
engine
example
block
for.
and engine block and the moving fluid will be the wind, sir.
Okay, wind or air which comes in contact. Okay, what are the modes of heat transfer which is associated with engine block and air?
Conduction and convection.
Conduction and convection. How you say conduction and convection?
So from the cylinder to the engine block will be conduction, sir.
Okay.
And from conduction to the air will be via convection.
Okay, very good. But how the cylinder gets heated? How the cylinder gets heated? Actually, the process inside the engine cylinder is combustion of air fuel mixer.
Exothermic, yes, sir.
Okay, combustion of air fuel mixer. So again, a high heat transfer from by means of convection from the hot gas to the cylinder. Okay, convection. Cylinder surface to the fin surface by means of conduction, and from fin surface to the upcoming wind or upcoming air is again convection. Okay, convection, conduction, and convection. Okay, and similarly in car radiators also you will be having a combo of convection and conduction. Okay, and whereas in case of steam pipes, okay, in case of steam pipes we will be having the hot fluid which travels inside, which flows inside. Okay, whereas which flows inside at a faster velocity, and the solid surface will be at a lesser temperature. Okay, and radiation, when we talk about radiation, we know that without any physical media, if the heat is transferred by virtue of the temperature difference between two bodies, then it is said to be radiation. Okay, so it is in the form of electromagnetic waves, emission of energy in the form of electromagnetic waves, that is said to be radiation. Okay, and similarly we also discussed about what is steady state and unsteady state. Steady state is the one in which the temperature doesn't vary, temperature of a body doesn't vary with time, whereas unsteady state we will be having the variation of temperature with respect to time. For example, unsteady state examples were dropping a hot solid inside a cold water. Okay, so to attain equilibrium, it will take so much time. Similarly, the heating of the earth's surface and cooling of the earth's surface. We know that the earth's surface get heated during daytime, okay, and it cools during night time. Okay, so again, heating and cooling of earth's surface is also an excellent example for unsteady state heat transfer. Am I correct or not? Am I correct?
Yes, sir.
Okay,
Yes, sir.
so in case of electric power generation, heat transfer problems must be solved. Similarly, as I mentioned earlier, for refrigerators, air conditioners, food industry, especially nowadays, that's what I said. The use of OTGs, okay, it involves the scientific concept of heat transfer. Okay, without heat transfer concept, you cannot achieve a great taste in your food, right? Whether you prepare whatever food items, okay, using the OTG, okay, or the oven, okay. So without the heat transfer concept, how much heat is adds has to be transferred, okay, to the food material which is placed inside, okay. So that is very very important, okay. And yeah, even in internal heat generation as well as unsteady state heat transfer, we will be solving some problems in that also, right? And we also discuss about how the first law of thermodynamics is related to heat transfer, etc., okay, in the last class. And similarly we also discussed about the units, and especially degree C and Kelvin, okay. When it appears in the denominator, the unit change does not affect the numerical value, okay. So that is also very very important, you should know, okay. And you should know the relations. So the first relation is very very important: Q minus W, which is equal to del U, or Q equal to W plus du by dt, okay. The heat transferred is equal to work done plus change in internal energy with respect to time, okay. So that that particular thing you should know, okay. And there are three basic laws which I had told you in the last class. Can anyone say what is Fourier's law of conduction? What is Fourier's law of conduction? Anyone can say?
So the
Fourier
heat
law.
flux is directly proportional to the temperature gradient and cross-sectional area of heat transfer.
Yeah, very good, very good. The rate of heat flow through a body or through a solid is directly proportional to the cross-sectional area, which is normal to the flow, and to the temperature with respect to the length of the heat flow, or to the temperature gradient. Okay, and Q is equal to Q is directly proportional to A into dt by dx, or Q by A. Q by A is nothing but the heat flux. That's what our one of our students did, okay. Q by A, it will be in watt per meter squared, okay. It is denoted by small q double dash, okay. Small q double dash, capital Q is heat transfer, okay. It indicates heat transfer, whereas small q indicates Q by A, which will be in watt per meter squared, okay. Heat flux, you can see here q, small q is usually mentioned in heat transfer rate, or heat flux, okay. Heat flux is it is denoted by small q double dash, or Q double dash, okay. So it will be in watt per meter squared, okay. And what about Newton's law of cooling? What about Newton's law of cooling? Of course, from the Fourier law of conduction, we get one property known as thermal conductivity. What is thermal conductivity, ma? Anyone? What is thermal conductivity? Anyone? It is usually defined as the amount of energy conducted
Sir,
through a
when it
body of unit area and unit thickness in unit time. Okay. So usually it is mentioned as, it gives us an idea about the conductivity of the material. Okay. It is the amount of heat conducted through a body per unit area, per unit thickness, okay, in unit time. Okay. So that is thermal conductivity, and this thermal conductivity varies, okay. It varies with respect to time. And we also know that Q equal to minus K into dt by dx. What is the why the K value is negative? Any idea why the K value is negative? Sorry, why we have minus K into dt by dx? Any idea? Q equal to minus Ka dt by dx, or heat flux Q by A is equal to Q double dash. Okay, Q double dash or Qx double dash. If you take only the x-axis, then x-axis direction alone, then it is Qx double dash, which is equal to minus K into dt by dx. What is the reason for that minus sign, ma? Anyone? It is again
Sir,
very very
related to
important.
direction, sir.
It is related to direction now. Yeah.
Heat
Actually,
exhaust, sir.
the thing is, it takes care, that is, the minus sign takes care of the decreasing temperature along the direction. We know that, see, when x equal to 0, when x equal to 0, T equal to T1. Okay, and when x equal to L, T equal to T2. Okay, or in other words, you can see here x equal to 0, T1, and x equal to L, T2. That is decrease in temperature. Okay, so when the heat is transferred along the x-axis direction from one end to another end, slowly what happens is, due to the thermal conductivity of the material and due to the thickness of the material, what happens is the heat transfer from one end to another end, okay, slowly it reduces. Okay, and due to this reduction, okay, that to take care of the decreasing temperature, uh, in the direction of increasing thickness, usually it is taken as negative. Okay, so finally we will be getting Q value, uh, total Q, which we will be getting, or the heat flux we will be getting in the positive value. Okay, so if we get it negative, means then what happens is, instead of heat transferring from T1 to T2, we have to assume it transfers from T2 to T1. Or usually the assumption is this side will be the highest temperature and that side will be the lower temperature, but sometimes it also happens in the reverse manner also. Okay, so sometimes if you have a hot body outside and a cold body, or sorry, if you have a hot fluid outside and if you have a less temperature plate, then naturally what happens is you will be having heat transfer. This is what happens in case of ovens and all, right? We will be placing the plate. Okay, the plate, initially when we place it, the plate will be at a lesser temperature, whereas the zone, you will be keeping into the hot combustion zone, okay, inside the oven. Okay, so it will be slight at a higher temperature. Slowly the heat energy is transferred from the hot wave or the uh, hot chamber inside to the vessel which you keep. Okay, so it depends upon so many things. Okay, so that particular thing you have to understand, why minus k, why the minus sign is there. Okay, the minus sign indicates the uh, um, decreasing temperature along the direction of increasing thickness. Okay, so that particular thing you should know. Okay, and similarly the resistance, when we talk about resistance, we know that Q, which is equal to Ka by L into Th minus Tc, or Q, this again we rewrite it as Q equal to Th minus Tc divided by L by Ka. So we will be writing like this. Okay, so yeah, I think yeah, it's already given in the slide itself, so no need to. Yeah, Q, which is equal to uh, Th minus Tc divided by L by Ka. This Ka by L, when it comes in the denominator, it becomes L by Ka, or in other words, Q equal to temperature difference divided by thermal resistance, or Q equal to thermal resistance inverse into temperature difference. Just like Ohm's law, I equal to 1 by R into del V. Similarly, we calculate here the thermal resistance. All of you are able to understand this? See, actually, uh, Q equal to Ka by L into T1 minus T2. Okay, so which we can rewrite it as a T1 minus T2 divided by L by Ka. So this L by Ka is nothing but the thermal resistance, T1 minus T2 divided by R Th, or del T divided by R thermal conductive resistance. Okay, so all of you are able to understand this. This is thermal
Yes, sir.
resistance, del T divided by thermal resistance. So this particular thing you should understand when we talk about thermal conductivity. Okay, similarly in case of spheres and cylinders, it will be you will be getting like that. Okay, you will be getting the surface area. You will be involving the surface area, natural log of R out by R in divided by 2 pi Lk. We will discuss that when we solve problems on it. And similarly, Newton's law of cooling. Okay, so Newton's law of cooling gives us an idea about the convective heat transfer. Okay, what it says, Newton's law of cooling. Anyone? Can you say what is Newton's law of cooling? What it states?
So that
The heat
that
transferred by means of convection is directly proportional to the It is directly proportional to the temperature difference between the surface and the fluid and the cross sectional area or the area over the flow. Okay, q equal to q directly proportional to a into del t, or q equal to ha del t, where h is nothing but the convective heat transfer coefficient. Again, it is an property which depends upon the fluid which carries the heat. Okay, and the convective heat transfer coefficient for liquids it will be higher, and for gases it will be slightly lesser. Am I correct or not? Newton's law of cooling.
Yes, sir.
Okay, Newton's law of cooling, what it says that the heat transferred between a surface and a fluid is directly proportional to the temperature difference between the surface and the fluid, as well as the area over which the fluid flows. Okay, cross sectional area over which the fluid flows. Okay, and q is equal to ha del t, where h is nothing but the constant, and that particular constant is said to be the convective heat transfer coefficient. Okay, and again, in case of q convection, we used to say like this, we used to write like this: q equal to ha del t, or del t divided by 1 by ha. That 1 by ha is nothing but the convective resistance. Okay, convective resistance, the convective thermal resistance is 1 by ha. All of you are able to understand this? Just like in case of conduction, we have L by Ka, del T divided by L by Ka, whereas in case of convection, we have 1 by Ha. All of you are able to understand this? Q equal to Ha del T, 1 by Ha is nothing but the convective resistance. Is this fine? Is it fine,
Yes.
ma? Okay. And you can look into the values. When we look into the values, you can see here for gases it is lesser for free convection, and liquids it is higher for free convection. Whereas in case of forced convection, the gases will be slightly higher and liquids will be much more higher, 50 to 20,000. And in case of phase change, that is especially boiling or condensation, we have the convective heat transfer coefficient, which depends upon how much heat energy is absorbed by the liquid, so that it gets converted into vapor. Okay, so it ranges from 2500 to 100,000. Okay, so why the h value, convective heat transfer coefficient value is higher in case of forced convection? I already told you the chai wala example in the last class. To cool the fluid, okay, when you keep the
Sir,
fluid,
external factors, sir.
yeah, the velocity which is imparted to the fluid is very, very important in case of forced convection. So Reynolds number, critical Reynolds number. Okay, Reynolds number gives us an idea. Okay, Reynolds number is equal to ud divided by nu, where u is the velocity which is imparted. Okay, u is the velocity which is imparted. Okay, so higher the velocity, larger will be the flow rate. Okay, larger will be the heat transfer rate. Okay, higher the velocity, larger will be the heat transfer rate. Okay, so that's why when even I have already told you about the practical cases. Okay, if you increase the voltage beyond a certain limit, in case of electric cables, sometimes the electric cables gets fused. Okay, because then that is the flow of electrons. Okay, if the rate increases very high, okay, then naturally what happens is again it will lead to fusing of the material. Okay, so too much of high heat energy, sometimes the cable will not be able to handle it, and what happens is, since if the heat dissipation to the surrounding atmosphere is not there proper, then automatically fusing occurs. Okay, so so it is for each and every practical application we use. Even in case of heaters, whatever heaters we use in our house, sometimes the heater, what happens is the fuse goes off. Okay, mainly due to over heating of the material. Okay, due to high voltage, what happens is the fuse that is the fuse material gets melt. Okay, so the effect of heat transfer coefficient when it comes to forced convection, it will be the values will be slightly higher. That particular thing you should know. And radiation, I have already told you the Kirchhoff's law of radiation. What it says is, sorry, Stephen Boltzmann law. There is a Kirchhoff law is also there. Okay, Stephen Boltzmann law. What it says is the emissive power of a body is directly proportional to the fourth power of its absolute temperature, and usually it is written as EB, which is equal to EB proportional to A T power 4, where A is nothing but the surface area and Ts is nothing but the surface temperature. And when we substitute temperature, we have to substitute in Kelvin, not in degrees. See, that particular thing you have to understand. Our EB equal to sigma. That sigma is nothing but the Stefan Boltzmann constant, which he from by conducting experiments he found it as 5.67 into 10 power minus 8. Even we have this apparatus, and we will be able to finding out the Stefan Boltzmann constant with one of the experiment. Okay, so these things you should know. Okay, and for real surface, E equal to the emissive power is equal to the emissivity and into sigma into Ts power 4. Okay, where emissivity gives us an idea about the emissive power of the given substance, and alpha, sometimes alpha absorptivity, some substance uh, will be absorbing more heat. As I mentioned earlier, black bodies is capable of absorbing more heat energy as well as emitting more heat energy, whereas gray surface and white surface reflects all the heat energy. Gray surface partially it absorbs, partially it emits. Okay, so you should know about this also. Okay, so especially the incident radiation. Okay, if you have observative value which is or observative which is denoted by alpha, then it will be in the range of 0 to 1. Okay, and similarly emissivity is also in the range of 0 to 1. Okay, except the white body. Okay, white body reflects all, it won't observe. Okay, so those things you should know. And for gray surface, you will be having this combo alpha plus tau plus rho, where alpha indicates observability, tau indicates transmissivity, and rho indicates reflectivity. Okay, so and for gray surface, alpha is equal to epsilon value or alpha equal to emissivity. Okay, and whenever we have this, you should know about all these things. Okay, when radiant energy is incident on a transparent surface, it can be absorbed, it can be reflected, or it can be transmitted. Especially when you take a glass surface, what happens is you will be having partially it will be absorbed, partially it is transmitted, and partially it is reflected. Okay, so these things you should know. Okay, and the remaining other things we will be discussing when we discuss radiation. Okay, so some small numericals will also be there, but I will not be doing numericals here. But I will even in cat 1 examination. Okay, you will be getting a small numerical. Okay, I will be giving you the H value and surface temperature and T infinity value. Ts is surface temperature and T infinity is nothing but the fluid temperature. Okay, so you will be asked to find out the heat conducted, heat convected, as well as heat radiated. Okay, so some using the small that is using these values, small numericals will be given. Okay, small numericals will be given, and you are expected to do it. Okay, and please don't ask us, sir, you didn't do the numericals. So just one step will be there. And as engineers, and especially in the 6th semester, you are supposed to do solve more numericals. Okay, and especially the first two things. Okay, the conduction and convection. Anyway, we will be doing composite wall or composite systems in the first module. Sorry, second module. So we, it's much more easier, and you will be understanding it in a better manner when I solve some problems here. Okay, and yeah, these things I have told you in the last class, or in the very first introduction class I have told you, and k value, everything. Now the next one is the heat diffusion equation. This is very very important, when we want to discuss this uh, heat transfer through a simple solid. Okay, we know that actually this particular heat diffusion equation, the how we get this is from the basic first law of thermodynamics. From the first law of thermodynamics, we know that Q minus W, which is equal to del U. What is Q? What is W? What is del U, ma? What is Q? What is W? What is del U? Yes, anyone?
So del U is change in internal energy, sir.
Uh,
Q
W
okay.
is heat
is
transfer.
wasted
W is
work
Work,
done.
work, like that.
Work done.
work done. Okay, fine. Okay. What about the Where is it?
Q is heat added to
transfer.
the
Okay,
Heat
Q is
transfer.
heat transferred. Okay, del U. And what about sorry, W is work done. Q is heat transferred. What about del U?
change in internal energy.
The change in internal
Energy.
energy. Okay. So from that only we will be getting this particular expression. Okay. Let me take the internal heat generation. I am having a yeah. Because that particular expression will give you much more better idea when compared to okay. Okay, ma. See, I will check that and I will give it to you in the next class. Okay. So now what happens here is the heat which enters your body is Qx, and the heat which leaves the body is Qx plus dx, taking into account of the distance dx. Okay. Assume the solid is having in the x-axis it is having dx, okay, the distance ds or the length dx, and in the along the y-axis it is dy, and along the z-axis it is dz. Okay, so assume that qx is the heat entering the solid, and qx plus dx is the heat energy which leaves the solid. Okay, now what happens is we know that q minus w, which is equal to del u. Some of the students you said it, q minus w, which is equal to del u, where q is nothing but the heat transferred, w is nothing but the work done, and del u is the change in internal energy. Now what is internal energy? The internal energy is the one which is because of its temperature. Okay, higher the temperature, higher will be the internal energy. Am I correct? Am I correct or not?
Yes, sir.
Higher the temperature, higher will be the internal energy. So now what happens here is, now we know that qx which is equal to minus k into a into dt by dx, or dou t by dou x, temperature gradient with respect to x-axis only. Okay, and qx which is equal to minus k into dy by dx. Okay, area, when we consider the area, see we know that along the x-axis the area, right, the area is dy and dz. The area which is normal to the flow, all of you are able to understand this? The area which is normal to the flow is usually considered. Okay, so the heat enters in this direction and it leaves in this direction. Okay, along the x-axis the area which is dy and dz. Am I correct?
Yes,
This
sir.
area, this rectangular area or the square area, dy by dy into dz. All of you are able to understand this? Why a
Yes.
is written as dy and dz?
Yes, sir.
Yes.
Yes, sir.
Okay,
Sir.
so the area which is normal to the floor is dy dz. Okay, minus k into dy dz into dou t by dx, dou x. Okay, and similarly qx plus dx is equal to this qx value plus dou q by dou x into dx, and it is similar for the y-axis direction. Okay, for example qy will be equal to minus k into a into dou t by dou y, and q is equal to minus k into a into dou t by dou z. Okay, so the other two direction it was not written. Let me write it here. So similarly for qy, which is equal to minus k into a into dou T divided by dou Y, and Qz is equal to minus K into A into dou T by dou Z. Now what happens here is, in this case, for Qy minus K into A, area will be dx dz, okay, into dou T by dou Y. And similarly for Qz is equal to minus K into dx dy into dou T by dou Z. Okay, is it fine? Is it fine, students?
Yes, sir.
Okay, so similarly for y directions, y and y axis and z axis, you should write that. Okay, because it is skipped in the slide. Okay, to reduce the number of steps, it is skipped. Similarly for qx plus dx, you will be having qx plus dou qx by dou x into dx, and as qy plus dy will be equal to qy plus dou qy by dou y into dy. Okay, and dz also, qz plus dz will be equal to qz plus dou qz divided by dou z into dz. Okay, so differential control volume dx dy dz for conduction analysis in 3D Cartesian coordinates. Okay, so when we have this, we will be having this, and we will also be having one more term, which is nothing but the internal heat generated. Okay, the internal heat generated is E suffix G, and that is mainly due to the flow of the heat. Okay, so that will be, as I mentioned earlier, right, when the heat energy increases, the internal energy increases. So the internal heat energy generated also increases whenever a body conducts. And that's what I told you about the electrical cables. Okay, the electrical cables gets heated, okay, or the internal energy gets heated whenever conductivity happens. Okay, so the energy Eg is nothing but the internal heat generated, okay, in all the three, dx, dy, and dz, and the stored energy. The stored energy depends upon the uh, density, specific capacity, as well as the volume. Okay, when we talk about the volume of the simple cube, which is shown here as, it is nothing but dx dy dz. Okay, rho cp dx dy dz into dt by dt. Okay, when you substitute this, finally when we know that q minus w, which is equal to del u, or the energy entering into the system minus energy leaving the system, plus the internal heat generated due to the movement of this heat energy through the through the solid, is equal to the energy stored. Okay, or in other words, where at a thermal equilibrium conditions, the energy entering the body, and minus the energy leaving the body, plus the internal heat generated due to the flow of heat, will be equal to the stored energy. Or in other words, dou by dou x of k into dou t by dou x plus dou y of k into dou t by dou y, and dou by dou z of k into dou t by dou z plus internal heat generated, which is equal to rho cp into dou t by dou t. Okay, so this expression will leads to the equation dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square plus g by k, which is equal to 1 by alpha into dou t by dou t. Now this is the very important heat diffusion equation, and if there is no internal heat generation, this g by k will be equal to 0, and if it is steady state condition, then dt by dt is equal to 0. And if we don't consider the heat transfer along the y-axis and z-axis, then these two terms will become 0. For one dimensional steady state condition, the final thing is 0. This particular thing is 0, and if there is no internal heat generation, then this term will become 0. So what happens then is, we will be having dou square t by dou x squared is equal to 0, or when you double differentiate it, we will be getting the expression for a simple slab. Okay, so this is very important. This particular equation is very important, and how we are getting this equation also in all the heat transfer data books, heat and mass transfer data, sorry, textbooks, you will be having this expression, how to get this expression. Okay, see, you have to start from this equation, and after starting from this equation, you have to write all the steps, and finally you have to get this expression. And what happens when What happens when there is no internal heat generation, and what happens when there is no uh, when there is steady state heat transfer? What is mean by steady state heat transfer? What is mean by steady state?
So change in temperature with respect to time. So.
Change in temperature with respect to there is no change in temperature with respect to time. Steady state means there is no change in temperature. The temperature won't change with respect to time. That is steady state. Unsteady state means temperature change will be there. Okay. No change in temperature with respect to time is steady state. So dou T divided by dou T, this expression will become 0, and the internal heat generation is also 0. Now when you take a small solid, okay, consider only the x-axis. So you have the general equation, and in case of a plane wall, if we have steady state heat conduction through a slab of thickness L and with no thermal heat generation and with constant thermal properties, then what happens is this and this particular thing expression will become 0, this will become 0, and only you will be having this. Let me write it here. I don't know how many of you understood that, or I don't know. So consider a solid slab. We have another 5 minutes time. Kindly bear with me. Assume you have a slab of thickness L, okay, and temperature T1 here and temperature T2 here, and usually you have to consider the area which is normal to the flow. This area only you have to consider. Okay, students? Students, is it clear?
Yes.
Yes, sir.
Is
Yes,
it
sir.
visible?
Yes, sir.
This particular area only you have to consider. The area which is normal to the heat flow only you have to consider. This is temperature T1 and this is temperature T2. Okay. Now L is nothing but the thickness. We know that the equation, three-dimensional equation is dou square T by dou x squared plus dou square T by dou y squared plus dou square T by dou z square plus G by K. In some textbooks, especially Rajput and all, they used to mention as QG by K, which is equal to, the QG is nothing but internal heat generation. 1 by alpha, 1 by alpha. So again, this alpha, I will tell you, it is thermal diffusivity. Dou T divided by dou T, where T is nothing but the temperature and small t is nothing but the time. Okay, so this is the expression which is given here. Okay, now what happens is, for one dimensional thing, we will be considering only x-axis, and if there is no internal heat generation, then this term becomes 0, and if it is steady state, this term becomes 0. So when it is steady state, this is 0. No internal heat generation, this becomes 0. And only one dimension, x-axis, these two terms become 0. Students, all of you are able to understand this, why all these terms become 0? For steady state, this becomes 0. Okay, students? Hello? Am I audible?
Yes, sir.
If there is no internal heat
Yes, sir.
generation, this term becomes 0. And when we consider only the x-axis, this term becomes 0. So now what happens here is, when you double integrate this expression, and we know that the solution will be temperature is a function of C1x plus C2. And when you apply the boundary condition, you will be getting it. Now, let me apply the boundary condition here. So when we double integrate, the solution is T equal to, the solution is T equal to C1 of x plus C2. This is the solution. Okay. When you double integrate, or dou square T by dou x squared, when you double integrate, you will be getting temperature. And when you apply boundary condition, we know that here x equal to 0 and here x equal to L. Am I correct, students?
Yes, sir.
0 to L. Okay. So when you, and at x equal to 0, temperature is T1, and x equal to L, temperature is T2. Okay. Now when you substitute the boundary condition, at x equal to 0, T equal to T2. Okay. So the first boundary condition when you apply in this expression 1, so x equal to 0. So this t equal to t2. Sorry, t equal to t1. T1 which is equal to C1 into 0 plus C2. So which implies C2 is equal to T1. Am I correct?
Yes, sir.
Am I correct, students?
Yes, sir. Yes, sir.
Simple mathematics. Similarly, apply the second thing. Okay, at x equal to L, T equal to T2. So which implies when you substitute that in the equation, T2 which is equal to C1 into L. Am I correct? C1 x equal to L plus C2. And already we know that value C2 equal to T2. Sorry, T1. So you substitute here and get, so which implies when you substitute this here, let me write it here. So which implies T2 is equal to C1 into L plus, what is C2 value we got here? C2 equal to T1, substituting it here. So C1 will be equal to T2 minus T1 divided by L. Am I correct? Am I correct, students?
Yes, sir.
Now substitute this C1 and C2 in the general equation. Okay, when you substitute the C1 and C2 in the general equation, you will be getting this expression Q equal to, so substituting it, you will be getting T temperature as a function of, see, I have taken T2, here they have taken TS2. So TS2 minus TS1, that is T2 minus T1 into x by L plus T1. Okay, so this is what we have got, T2 minus T1 into T2 minus T1 by L into x plus T1. Am I correct, students? T2 minus T1 into x by L into sorry, plus T1. This is the final temperature. Okay, so now we can rewrite this again as, we know that Fourier law minus k into a into dt by dx, which is equal to k into a into T1 minus T2 by L, or which is equal to T1 minus T2 divided by L by Ka, where L by Ka is nothing but the thermal resistance. Okay, so the thermal resistance you have to find like this. Okay, so in the next class what we will be discussing is, we will be discussing the for a composite wall what it will be, and we will also discuss about the combination of thermal conductivity as well as convective heat transfer coefficient. Okay, so in the next class we will be solving some numericals. Okay, that is tomorrow I expect all of you to join by 8 o'clock itself. Okay, so with this I stop the recording.